Good afternoon. Can you hear me? Please confirm.
Yes, sir, you're audible.
Okay, thank you. Let me share the screen. It's too cold here. I'm facing difficulty to even move my fingers. Current slide. Okay, so let us start. You can see people are still joining, but it's already too so I have to start. So I think you have some of you have watched the video that I have uploaded on main memory. So when I uploaded, I have mentioned it also that the video that I have uploaded on main memory is not directly connected to your course. Maybe some of the slides, some of the point that I have mentioned in that video will be required, but that I'll separately mention whenever it is required. I'll separately mention it. At this moment, if you have watched that video, that is only for your information. If you have, to understand how main memory works, and in future, if you want to do more work, and maybe if in future in after mid semester when you will do project, it may help you, but not directly connected with your course. So I'll do this type of recording. I have some similar recordings, and you can see that the video that I uploaded was the advanced level course. It was designed for BTech final year, MTech, and PhD students. So I have some more interesting videos like this. So maybe in every 2 weeks I'll upload some similar videos. You can check those videos also. But anyway, it is completely your choice. If you don't watch those videos, it's not at all a problem. Okay. And last class I also promised that I'll upload another short video to complete the introduction part, but later I dropped that idea. I thought, no, let us complete the introduction part in live sessions only, and if it is required, then maybe in this week during the tutorial I'll take one lecture. May not be a full 50-minute lecture, maybe just a 30-minute lecture to complete all the pending tasks, and then I will today I'll complete the introduction part, and tomorrow only I'll start from the textbook. So previously I was planning to explain only there was only 2 slides in this PPT remaining at that time. So but at that if I do that, then I have to start your textbook in the middle of today's lecture. But I don't want to do that. So what I did, I've extended this PPT. I have added few more slides, and then I will complete all the introduction part today, and from tomorrow directly start from textbook. So all these things that I have explained, that I am discussing now, which are not directly from textbook, don't think that these are useless. These are important, and you have to watch them properly. And after this week, next week you will have a class test, and in that class test, mainly the main course, mainly I'll ask from the concept that I'm explaining now. Okay. And if you understand all these initial videos that I am now discussing, then it will be easy for you to understand the textbook, because there are many concepts written in the textbook. So when you read the book, then it will be easy for you if you know the concept, because almost a basic an introduction I'm giving about the entire computer, how it works. So CPU part I've explained, and last class I end in this point that how memory part works. So today I'll mainly explain how memory parts works. So memory means, let us start with a core. So suppose if this is your CPU, or you can say this is your core. Suppose this is a core. Why I'm saying core? Because maybe you know this term called multi-core processor, quad core, dual core, octa core. All these terms are known to everyone nowadays. So suppose this is your processor name is C1, and then when I have designed this circle, you assume that within this circle, all this thing like the control unit, arithmetic logic unit, everything, and registers, everything is inside this circle. So why most of the time I'll use this type of diagrams in this course. So that's why I'm explaining it here. Every time if I make a circle like this and I say this is a core, at this moment you have to understand there is not much difference between processor and core. Yes, there are difference, but I'll discuss it later. So what is inside this circle? So the concept that we understood in previous classes, like registers, arithmetic logic unit, and control unit, everything is inside this circle. And outside this circle, you see there is a box. I said you can say this is a cache memory. So if core requested for a data, first it will request to its cache memory, right? So cache memory also has multiple levels nowadays. So if this is L1 cache, maybe after it there will be a L2 cache, and then there will be maybe a L3 cache, which is even bigger. L3 cache, and combining all these things, this is your processor. This is your processor chip. That's why I said that the cache memories are part of the processor, not outside the processor. The RAM is outside the processor, not cache memory. So this outer box is your processor. So in your processor, so the main component of processing units are there, that is register, arithmetic logic unit and all. But with that, the memory units are also there. Memory unit means cache memory. Okay, so that's why I have written here cache memory placed on chip, and there are cache memory like L1 cache. L1 cache is divided into instruction and data cache that I will discuss later. At this moment, I will not explain it. So L1 cache, L2 cache, and then L3 cache. So see, there is a term called last level cache. We normally call it LLC. So LLC means here LLC is L3. So if you some of the processor has only two level of cache, only L1 and L2 are there. So we'll call L2 as LLC. LLC means last level cache. Here LLC is L3 because there are three levels of caches. Okay, and then outside this box, this is the processor. Outside this box you have main memory, which is RAM, and then you have secondary memory, which you normally call as hard disk or SSD. Okay, so now when we'll try to understand the cache memory, I will not consider multiple levels of cache memory like the L1, L2, and L3. I will not. I'll only consider a single cache. There is a core and there will be a cache, and then there is main memory and hard disk. I'll assume this. So let us remove all these things from here. I'll not consider multiple level of cache. I'll consider this diagram to explain you cache memory. You can see this box is your processor. Inside this box there is a core name is called C1, and then there is a cache memory inside this. So only one level of cache memory, and outside that cache memory you have a main memory. Here you can see this box is your main memory, and inside this main memory there are some data present. So I represent those data as A, B, C, D. So these are just the representation. So I am representing the data in this format now. Okay, I think here before I should start cache memory, let me explain this. I think I have explained it, right? Principle of locality, temporal locality and spatial locality. So the principle of locality means if this core or this core is requesting for some data, then it is highly likely that in near future it will request for the same data. That is called temporal locality. And if this core is requesting for some data, then it is highly likely that the in near future it will request for the nearby data. That is called spatial locality. So temporal locality, spatial locality I have explained. Then let us move to the next slide. So before explaining how cache memory works, we need to understand some basic terms. So principle of locality is temporal and spatial I've explained. Some more important terms I need to explain here. Then we'll start. Okay. So now in non-technical way, if I say how computer works, first, if core will request for some data. Why? Because if you remember in the first lecture I said computer follows von Neumann architecture. So every data is initially in your memory, and one by one the data has to move from memory to core, or at that time I said processor. So one by one you have to move data from memory to core, and then all the operation are performed in the core, and then finally at the end we have to write the data back. So there is a communication is required. So first time when core will request for a data, where will search the data, will search the data in the cache. So that, and if the data is found in the cache, we call it a cache hit. And if the data is not in cache, then we will have to go to main memory, and from main memory you have to fetch the data. Okay, so what is the difference? If there is a cache hit, then it will save time, because if cache is on chip memory, it's very fast. If the data is not in cache and you are going outside the chip, which is main memory, then it will take or at least 1,000 cycles more to fetch the data in the cache. That's why cache is important. Okay, so the basic is clear. Now, the term that I said, core request for data. Actually, why in if we go in more technical way, what is actually requesting by the core, right? So core is requesting for a word. Word means word contains 8 byte. So suppose the last class I explained, right, what is called bit, what is called byte. So assume that a word has 8 byte. So every time core is requesting for a 8 byte of data. Suppose. Okay. So this is called core. That's why I've written core always request for a word. So core request for 8 byte of information. So now let us start. I think let us start from here. If you can see there is a sequence written A D A. Na? So this sequence is you can assume this sequence as the sequence where the in which the core is requesting for the data or core is requesting for what. So first time the core is requesting for A, and where are those data actually? You can see data are initially all data are stored in main memory. A B C D all are words actually. A is the first word, B is the second word, C the third word, right? Like this. So first time core is requesting for a word called A. So you can see first of all it will search the block in the local cache. You can see nothing is there in the cache, so there will be a miss in the cache for A. So we'll go from here to main memory, and from main memory, yes, A is there, so you have to bring A or to fetch A from main memory and have to store it here, right? But we will not do that. When we'll fetch data from main memory, we will not just fetch A. With A we will fetch this entire thing and we'll fetch it here, A B C D, and then from here we'll return A. It will fetch here, and from here we'll return A to core. So now the question is why, when the core is requesting for a word, why we are going to main memory and fetching a complete a bigger chunk, not just a word? Because of spatial locality. Because if it is written here, I said now, if the code is requesting for a block, now it is very likely that in near future it will request for the nearby blocks. So in near future, it is highly likely that it will request for B, it will request for C, or it will request for D. That's why when we'll go to main memory, we'll fetch a bigger chunk. That bigger chunk is called cache block. So you have to remember this term, cache block. So every time when we move something from main memory to cache, that is always in form of block. We call that as block, and a block has multiple words. Normally block size normally 32 or 64 bytes are very well known. So always remember, every time whenever I'll write capital B like this, you have to assume that this is byte, not bit. It is byte. So normally block size ranges from 32 to 64 byte. Here I am assuming a block is 32 byte. Why I'm assuming 32 byte? Because each word is of 8 byte, I'm saying. And how many words are there in a block here? If you see the first byte here, the first, this is block, this is block 1. Suppose block 1, this is block 2, this is block 3, block 4, block 5. So in first block you can see there are 4 words, so 4 into 8, that so block size is 32 byte. Now so let us go for the next request. Now after A, C1 will request for D. So when C1 will request for D, then first request will come to the cache, okay, and the D in cache. So it will be a cache hit. You no need to go to main memory. You can save time. So here it is called cache hit. So from cache only, D will be supplied to C1. Okay, so this is done. The same thing will be for A, right? So when if after this, if core will again request for A, then it will be also served from the cache. So you can see when it is requesting D, you can see as I said, according to spatial locality, it is requesting the nearby core. When it is requesting for A again, you can say this is because of temporal locality, it is again requesting for the block A. Okay, after A, it is requesting for F. So when this core will request for F, then suppose this is requesting for F. Now F is not in cache, so you have to go to main memory and fetch, because this will be a miss in cache. So there is a miss in cache, so we'll go to main memory. From main memory you have to bring F, but will not just bring F, will bring the entire second block. Block 2 will be moved from here to here. E, F, G, H. The entire block is now in cache. And from here, then F will be supplied to the C1. The same thing it will continue when next it will request for L. When it will request for L, again you can see the L is not in the core, so I have to go again to the main memory and fetch the complete third block here. Third block is okay, I, J, K, L. There is some so third block is up to here. There are some mismatch here, but I hope you are understanding it. IJK. So complete block will be moved here, and then in this way it will perform the operation. So I hope from this point, I think what is called core request for a word, that point is clear. What is called cache block, it is clear. A cache block has multiple words. What is called cache hit, what happens in cache hit, it is clear. What is called cache miss, what happens when there is a cache miss. I think all these things are clear. And there is a huge timing difference between a cache hit and cache miss, because if there is a cache hit, then we'll only need to access the cache, and cache access time is very less. But if we want to go for main memory, when in case of cache miss, then we it's need a huge time compared to a cache hit. Okay. And cache replacement at this moment I'll not discuss it in detail, but only I'll say that, see, the cache memories are actually very small in terms of main memory. In a modern processor also, you'll have 4 MB to 8 MB cache. And you know the RAM size. RAM size nowadays varies from 8 GB to 16 GB in a desktop computer also. So you can see how big a RAM is as compared to cache. So obviously the cache will fill quickly. And once your cache is completely full, at that time, if the core will request for a new block, that block is not in the cache now, how you will place that block in the cache? You have to remove some existing block from the cache, right? So that is called replacement policy. There are some replacement policy based on which, because you have to decide cache is full, you want to remove some block to place new block, so which block you have to remove, that is called replacement decision, replacement policy. There are different replacement policies possible. A well-known replacement policy is called LRU, least recently used, means the block which is used in the oldest time. So the oldest block, always remove the oldest block. This is called LRU. So we'll discuss all these things when we'll discuss cache memory. So yes, one important point here, don't think that this is the last time I'm explaining cache memory. No, it's not like this. I'll explain cache memory after discussing the initial CPU and all from the textbooks. So basically, when I'll follow the textbook, I'll also explain you cache memory. But when if you'll have some idea about what is instruction, what is cache memory, then it will be easy for you to understand the concept even from the chapter 1. That's why I'm giving you an idea what is cache memory. Okay, then some more low level concept here. Till now I said that core will request for a word. Okay, fine, core will request for a word, that we can understand. Then if first of all we'll search that if the core is in cache or not. If the core is not in cache, then we'll go to main memory. Suppose the core is requesting for A. At that time, you will say that A is in the cache. Yes, A is in the cache. But how? Till now, we only understand it in a diagrammatic fashion, right? I have written A inside the box of cache. That's why you can say that, okay, A is inside. When core will request for Z, I have not written Z inside that box, so Z is not there. But that is very non-technical, right? How? Let us go even some more technical way. So before understanding a technical way, you have to understand this concept of memory address. The main memory is byte addressable. So now concentrate on main memory. Then in main memory, there are some data stored. So every byte is addressable, means there is a specific address for every byte in main memory. So how we can start is, see, if you can start A from suppose from 2000, if it is starting from 2000, so how many bytes A is taking? A is taking 4 bytes, right? Because it's a word, right? Don't think it's a English letter. I'm just assuming it's a word and I'm representing it as a English letter here, A. So A needs 4 bytes. So address of B will start from 2004, right? Like this. So it means that every byte has an address. It's a byte addressable memory, main memory. So now when core request for a word, what it will request? It will request for an address. It will request for the give me that address. I means what number this, or so what is called word address. See here, The address of this word is 2000. If I be request for B, then address of this is 2004. What is this 2004? 2004 is the first address of the first byte in the word, because A has 4 byte, right? 1 2 3 4. A has 4 byte. First byte address is 2000. Then it is 2001, 2002, 2003. Then B has again 4 bytes, right? First byte is 2004, right? Then second byte, third byte, 2004, 5, 6, 7, like this. Then C, first byte of C is 2008, right? So when I'm saying word address means first byte of that word, first byte of that word. So when core will request for A, actually core will request for 2000. Core will send a request for 2000. Then I want word from this address 2000. Okay. When core request for B, core will request for 2004. In this way, it will request. Okay. And one more thing here. I hope the word address is clear. Now we'll go for block address. You can say there are 4 words in a block. So what is called block address? Both 2000 and 2004, they are from same block, isn't it? Because A and B, 2000 is A and 2004 is B. I have just explained you. So both 2000 and 2004, these two memory address are from same block, right? So what is the block address? Block address means address of the first word or address of the first byte in the block. So if A, B, C, D, let us zoom this A, B, C, D here. This is your A, B, C, D. So this is a block. And this block has 4 word. 1, 2, 3. There are 4 word, right? Each word has 4 byte again. Right? So there are multiple bytes here. And I'm saying total 32 bytes are there. So block address means address of the first byte. Address this. So the first block address is 2000. What will be the address of the second block? Second block is here. Second block address will be I think 2032, because the address of the first is 32 bits are required. So second will start from 2032. So you have to understand what is called block address. Block address means address of the first byte in the block, and word address means address of the first byte in the word. So 2000 and 2004 that the core is requesting, both are from same block. Which block? Block address 2000. And the address of that block will be 2000. So now let me explain it more detail how computer will work. When core will request for A, suppose the blocks are not here. When cores will request for A, it will request for 2000. That is fine. It is clear. But when core will request for B, then it will request for 2004 here, right? Here B is not in cache. So we have to send a request from here to here. At that time, which request you will send? We will not send 2004. At that time, we will not send word request to here. At that time, we will send the block request. So at that time, we'll again send 2000, because this is the block address. We'll not send word address below the cache. We'll send block address. So after 2004, if it is request for C, which address is 2008, then I think suppose core is requesting for 2008, and at that time also assume that the block is not in cache, so we have to again go to main memory. At that time also we'll only go for 2000, because 2000, 2004, 2008, all these words are from the same block. But now I think if core is requesting for E, suppose core is requesting for F, so it is F will be 2036. No, not 20. No, sorry. Let us not confuse you. Suppose C1 is requesting for F. So if C1 is requesting for F, then F is not in cache. So we have to go to main memory. So what will send? We'll send the block address. So block address will be the address of the second block, which is 2032. I'm saying. So now the main intention here is to explain you that there is a difference between word address and block address. And every time when we go to main memory, we fetch a block. So you have to understand what is called block address. Block address means the address of the first byte in the block, and word address means address of the first byte in the word. So if you understand these 2 points, it is remaining thing is will be easy for you. And if any point is not clear, I'm advising you can ask question to me, or also you can watch this video again And then also, if it is not clear, you can always send me an email, or you can ask your question in Google Classroom also. Okay, so now normally there is a question. Cache memory also stored which blocks are present in the cache. One more. Let me. Okay. Cache memory also store which block are present in the cache and the address of that block in the cache memory. Obviously, otherwise, how can you search, right? If cache memory will not store the address of that block in cache, then obviously we cannot search. But as I said, one by one, I'll discuss all these things. Most probably, I'm discussing that point now. Uh, so I said address. So normally, you addresses are assume that all these addresses are 32-bit addresses. So if all the addresses here are 32-bit addresses, so it means that the address of A, address of B, address of C, all are of length. The length is 32 bits like this. So 32 bits are used to address to for the addresses here A, B, C, D, all. Okay. So now when your core will request for a block, suppose it is requesting for 2008, so actually it is not like this. So actually this address is actually 32-bit address. So 32-bit address will be here, and from that 32-bit address we have to first find out which part is called block, which part is required for block. Then there will be some part for set index, and then there are some part is called tag index. Based on this tag we compare. So all these things I'm not explaining in this slide. If you are not understanding this part, then it is also not a problem now. So that's why the question that is written here, that how cache memory store address, maybe I'll try to answer it today, and if it is not possible to answer today, I'll explain it in next class. Why? Because I want to go sequentially. I cannot just directly explain something which is which I have not discussed yet. Otherwise, maybe who is new in computer architecture will face problem. I'll answer your question. Okay, so all these basic concepts are now done. How cache memory works, cache hit, miss, all concepts are clear. I think here there are some important points about cache memory. These points are you just need to remember. Design technology, cache memories are designed with SRAM technology. So if you have watched my extra video that I have uploaded, in that video I think I at the beginning I said that main memory or RAM are designed with DRAM technology, right? And cache memory are designed with SRAM technology. So basically, what is called technology? Technology means the technique by which you can store one bit of information, because memory means storing the information, and all informations are in binary, right? So memory, if you want to design a memory, you have to find a technique through which you can save either binary 1 or binary 0. If you have two techniques, suppose this circle is for storing binary 0 and this square is for storing binary 1, then you can just replicate your technique and you can create a memory. So this is what this technology, the technology which we use to design a cache memory, is called SRAM technology. Okay, then block size. I think I have already explained what is called block size. The basic unit of cache storage. Core request for word. Core always request for a word, and multiple words stored in a block. Some important concept: cache hit, cache miss. I have already explained. Miss rate is miss per memory access. That I will explain later also. But miss per memory access. What is called memory access? Every time you want to search something in cache, that is called memory access. Every time you want to read something, or every time if you want to write something in the cache, that is called memory access. So miss per memory access is called miss rate. And cache hierarchy, I think I have explained you what is called cache hierarchy, that L1 cache, L2 cache, L3 cache, that I have explained, that is called cache hierarchy. We'll discuss more about cache hierarchy when we'll discuss cache memory from textbook. Now let us discuss CPU execution time. This is a formula. CPU. Last class I explained you CPU time, right? And at that time I said CPU time is CPU clock cycle into clock cycle time. If you remember, I said CPU time, and I mentioned CPU time equal to CPU clock cycle. That is total cycle required in CPU multiplied by time of one cycle, right? So if you have a core like this, if you have an application which you want to run in this computer, but let us zoom this computer. This computer has a core, right? So actually this application is running in the core, and then you have multiple level of if you have, suppose you have a cache memory, you have suppose two level of cache memory. So this is your processor, and then you have a main memory also, suppose. So it's not always necessary that CPU cycle. When I said CPU clock cycle, it means total cycle required in CPU. But if there is a miss in CPU, if there is a miss in your upper level cache, suppose L1 cache, then you have to go to lower level memories, like either in L2 cache, or maybe you need to go to main memory. So when you are in main memory and you are fetching data from main memory, it takes long time. At that time, you are not doing anything in CPU. So that cycle is not included in CPU cycle. Also, suppose you have written a C program, matrix multiplication program, and there is a scanf function is there. And scanf function is saying that you have to enter two values, like enter values, right? So you are entering values to keyboard. You are very slow, because as a human being, we are very slow compared to computer. So at that time, your CPU is all idle. So the cycle that we are wasting when we are typing something through keyboard, that time you cannot count that, okay, my CPU is slow. You cannot say this, right? So CPU cycle means total time that actually takes in the CPU to execute your program. Okay, and then extra time, this is sometime is called when you are typing something from keyboard, that is called input output time. Even if there is no input output through keyboard, then also suppose if there is a miss in L1 case, then you have to go to lower level memory. So that time is extra. So that's why the actual CPU execution time means, if you have a computer, and in that computer, if you want to run a program, or if you want to run an application, what is the actual CPU execution time? CPU execution time here is total cycle required in CPU, and then total cycles required for memory stall means the cycles required to fetch the data from memory to CPU. So total cycle required, and so this is your total cycle required in CPU, and total cycle required to fetch data from memory. So this is your total cycles, and these cycles you have to multiply with the cycle time, then only you will get the CPU execution time. Okay, so now what is memory stall cycle? How can you derive a memory stall cycle? So memory stall cycle you can also derive like this. If you know the number of misses, and miss penalty means the cycles required to fetch one memory block. If there is a miss in cache, or if I assume that there is a single level of cache here, so if there is a miss in cache, then I have to go to main memory, right? So if fetch it is taking suppose 200 cycle, if there is a miss in L1, I have to go to main memory and fetching a data from main memory taking 200 cycle. So miss penalty is 200 cycle, miss penalty is 200. So what is the memory, what is the total memory stall cycle? So total memory stall cycle will be total number of misses into miss penalty, or the cycle required for each miss. So in this way you can calculate miss stall cycles. And there is one more is called you can extend this like this. So number of misses you can so miss penalty I have directly written here. Now instead of writing number of misses, suppose there is IC means instruction count. I think I have explained it in last class. Instruction count means when you are running an application in computer, you are not running a C program, right? Ultimately the program is converted into some instructions, and that instructions are executed. So when you will execute a program, some number of instruction will execute. So the total instruction that is executed when you run a program, that is called IC, that is instruction count. So if you know the instruction count, how can you calculate miss per instruction, right? If you multiply instruction count with miss per instruction, then you will get number of misses. Sorry, number of misses. And now I'm going even further. Now I know instruction count, I know memory access per instruction. Then what? Then miss rate. What is miss rate? Miss rate is miss per memory access. So from here I'm getting total instruction, from here I'm getting memory access per instruction, and from miss rate I'm getting miss per memory access. So combining these three, again I am calculating number of misses and into miss penalty. So, and then there is a well-known term called average memory access time. It's called AMAT. This is very important term when we try to measure the performance of memory. So AMAT is calculated as hit time plus miss rate into miss penalty. I am not discussing it in more detail, because as I said, when we'll discuss cache memory, we'll discuss everything. So here my intention here is why I am showing this formula to you. Don't try to remember this formula, don't try to memorize this formula. It's not like this. Try to understand this formula. Why CPU execution time is CPU clock cycle plus memory clock cycle, and why it is multiplied with clock cycle time. You have to understand it. Memory stall cycle, number of misses into miss penalty, then number of misses can be extended with instruction count, miss per instruction. Each and every line, try to understand why it is written, why it is correct. Don't memorize it. There is no point to memorizing these formulas. It's not like that I'll give a problem and it will be completely fit on these formulas and you will just calculate it and find the values. There will be no question like this. You have to understand why these formulas are coming. Okay. So I think all the basic concept of cache memory is clear. Only one concept remains. It's called structure of a cache. Because till now I have just shown you a rectangular box and I said that is your cache memory. But actually it's not true. What is the internal structure of a cache? There are three types of cache possible. One is called direct map cache, fully associative cache, and set associative cache. But today I'll only explain you set associative cache. Direct map and fully associative I'll not explain today. I'll explain it later. So what is fully associative cache? Fully associative cache, you can assume like a 2D matrix like this, or a 2D array. Assume there are multiple rows are there like this. And there are columns also like this. Okay. So these are called set. These are set. Each row is a set. And these are called your ways. How many ways are there? 1, 2, 3, 4. I'll go with 4 ways. Oh, sorry. Somehow there are 5 ways, so let us go with 5-way associative cache, but actually it should be 4-way associative. But since there are 5 ways, I'm saying associative cache. It's a 5-way associative cache. There are 5 ways. So I have to remember that sets, rows are called here set, and columns are called here ways. So this is a structure. So each entry here, this location, here we store a one block, one cache block. We can store one cache block in each entry. If you consider this as a 2D array, then each block is a entry, right, of the array. So each entry you can store one block. Now as I said, that core is requesting, if this is your core request for a word, right, and word, but here word will be converted to a block address, and block address are also 32-bit addresses, right? So based on this 32-bit address, first of all, you have to map, because see, cache is also a big memory. 4 MB memory is not a small memory. It's not possible that every time you have to search the entire cache to find out the block. So first of all, every block, there is a mapping policy. In set associative cache, every block first map to a particular set. That either if suppose block A, first suppose block 1, block 2, block 3, there are 3 blocks. So if block 1 is mapping to this particular set, then it will always map to this set. You cannot move block 1 from this set to another set. So first of all, when code is requesting for a block, from this 32 bit, that I will fix some bit, and based on those bit, we'll first fix that, okay, in which set it is going. And the block can be only placed in that particular set. So now how we'll map it? Suppose there are 1024 sets here. I'm saying there are many sets here, right? Many rows. So assume there are 1024 sets. So how many bits are required to uniquely identify a set? 10 bits are required, right? So if this is your 32-bit address, this is your 32-bit address. So from this 32-bit address, there will be 10 bits here. These 10 bits will be reserved. This 10 bit will represent the set index. If this 10 bit is saying that, okay, the value of this 10 bit is 5, though, this block will be mapped in set number 5. If this value is 6, then this block will be mapped in set number 6. And only in set number 6 we will search it. This is the property of set associative cache. A block always mapped to a particular set, and will only search in that particular set for the block. Till now I have not explained how to search, how to store addresses and all. That part I'm not explaining today. I'll explain later. Normally there is a part called tag. That tag is normally stored in with each block, and when we search in that block, we'll try to compare this tag part. If there is a matching with tag, we'll say it's a hit. If there is no matching with tag, we call it miss. But that part I will not discuss now. Today, if you understand what is called set associative memory cache, then it is enough. You have to remember this 2D structure. You have to remember that rows are actually set, ways are actually column. 5-way associative means there are 5 ways. Four-way associative means four way. Normally associativity like 2, 4, 8, 16, 32 in this way we consider. Five-way is not practical, but since I have designed it wrongly, so I'm saying it five-way. Okay. So set associative case is done. Direct map, fully associative case, how advantage, disadvantage, everything will be discussed in this course, but not today. Data mapping, block searching, block placement, block replacement. I'm not that block searching. I said you have to search only a particular set here, and if the block is not in this set, then it will be a miss. And how to search based on tag? As I said, this tag will be stored here, and we'll try to compare the tag. Tag match ho gaya means hit, otherwise it's a miss. Block placement means where to place the block. So as I said, it will be placed within a particular set. And block replacement, if the set is full and another core is requesting for another block which is also mapping to the same set. Suppose ये set full है आपका, and now core is requesting for a block that is also mapping in this set, then it means that you have to remove something from this set and to end up and to place the new block. In that case, even if there are some free space available here, you cannot put it there, because mapping policy is saying that the new block is also need to place in this set. So jo jahan pe place hoga wahi pe hoga. Even if there is a free space there in some other set, you cannot move it. Okay. So set associative cache ho gaya. Now I think I have few, I think 10-15 minutes I have. So now I'll quickly explain the cache architecture of modern processor, because modern processor have multiple cores, right? We know the terms called dual core, quad core, all these things. Dual core means there are 2 cores within the processor. Quad core means there are 4 cores within the processor. So what is called core? So the first slide on the first lecture or second lecture, the concept that I explained, that there is a C, there are some register, there is a arithmetic logic unit. So that part you can consider as a core. So in this way, this concept that I said, that is actually it's actually replicated in a processor, and there are multiple such cores nowadays possible. So that part, that computation part is replicated nowadays. So yes, low level, if I go low level, there are more technical details, but I'm not going to low level today. So that's why you can see the left side diagram. I am assuming that this complete thing is a processor here. This complete thing is a processor. So in this processor, there are 2 cores, C1 and C2. Both core can perform independent operation, right? Suppose this is your computer, actually. This is the processor of your computer, and you want to run 2 applications. Application 1, it's an MP3 player. You want to play a MP3 song. And second one is, suppose you want to do some calculation, or you want to run some other application. So one application will run in core 1, and you can run another application in core 2. Even if you are not doing it, when you click 2 application in your computer, your operating system will do it. And in OS case, means even if your computer is not doing anything, then also in your computer a application is running, right? That application is called operating system. So even if you are just playing MP3 song, maybe MP3 song is playing in core 1, but in core 2 your operating system is running. So that the main purpose of multi-core processor is you can do multiple tasks simultaneously. So till 2000, when from 1992 to 2000 till 2000 or 2001, the industries were only concentrating on how fast a processor can be. Means most of the processor till that date was single core processor. There was only 1 core, and people are trying to create how fast a computer possible. I mean 2 megahertz, 2 gigahertz, 4 gigahertz, 5 gigahertz. How fast a computer can be made? How fast means how many cycles possible per unit time. So जितना ज़्यादा cycle possible होगा per unit time, उतना ज़्यादा fast execute कर पाएगा in a program. But from 2001, people stop thinking in this direction. You can see nowadays 4 gigahertz, 5 gigahertz, or 7 gigahertz processor is almost not there, right? So what was the problem? We've reached a threshold in 2001 that we find out that it's not possible to increase frequency because of heating issues, because chip will be very, very hot after if we keep on increasing the frequency, and maybe it will damage. So at some point we have to stop. And in 2001 or 2000, people realized that no, we cannot continue like this. We cannot simply increase the frequency and design faster computer. That's not a solution. There should be a threshold. So what is the solution? So the solution was, instead of going for a very, very powerful core, let us go with moderately powered multiple cores. So that's why suppose this computer has 2 cores. So maybe, and suppose there is one more computer which is only one core. So suppose this is running on 4 gigahertz, but this is running on 3 gigahertz is core. So then also it is beneficial. The multi-core is beneficial when you are running multiple program at a time. When you are running multiple program at a time, you can perform multiple job, you can complete multiple job much faster, because here even it is 4 gigahertz, you can only run a single application there. So the purpose of multi-core architecture is not to improve the efficiency of a single application. Maybe a single application will not run faster because if the frequency is less, but you can run execute multiple application at the same time. One will run in core 1, another will run in core 2. If you have more cores, then maybe another will run in core 5 or 6, like this. Normally number of cores like 4 to 2, 4, 8. Even the server computer has more than 100 cores are also possible in modern computers. So I hope the basic idea of core is clear. So you have to remember one term here called CMP, or chip multiprocessor. CMP, maybe I'll use this term in this entire course multiple times. CMP, so chip multiprocessor means within a single chip your entire processor is designed. Means if you have core, two cores, then the core, the L1 cache, then the L2 cache, and the wires to connect all these components, everything is in a single chip. That is called chip multiprocessor, or CMP. So as I said, this is your processor. Don't think that the only C1 and C2 are processor. When you go to market and you purchase a Intel i7 processor, you will purchase the entire box here that I'm saying, entire thing. This entire concept, all the cores, their L1 cache, the last level cache, their interconnects. Their interconnects means the wires. Everything will be in that chip. That is the processor. Last level cache. Last level cache, you can see here each core has a one L1 cache here. The L1 cache is private to each cache. Okay, private means it is only for that core. So this L1 cannot be used by C1, right? This L1 cannot be used by C1, and if I consider this L1 cannot be used by C2. So those are private to each core, and both the core are sharing a L2 cache here. So this L2 is also your LLC here, last level cache. If there are three levels, then what will happen in three level cache? C1, C2 will have private L1 and L2, and then last level will be shared. Normally, the last level cache is shared among all the cores. And you can see there is a matrix, a 2D array-like formation here. It means that it's a set associative cache. But for in case of L1, I have not shown any structure, but you also need to assume that L1s are also set associative cache. So AMD cache that I'm showing here are actually set associative cache. Okay, but even as I said, modern day, the cache memory, basically the last level size cache varies from 4 MB to 8 MB. So these MB, 4 MB to 8 MB are not a small size memory. This is a very huge memory in terms of searching time. If you want to search complete 4 MB space of cache, is not a easy task. So that's why in modern day, the last level cache is not looking like this. The last level cache looks like this. Actually, you can see this is actually the modern day last level cache. The last level cache is actually divided into multiple parts. Each part is called a bank. So the last level cache is divided into multiple banks. You can see there are multiple banks here, and those banks are connected with some wires. And those wires, there are some small circles here, right? These are called routers. As the concept is called NOC, network on chip. That is a very high level concept, and it is not required for this course. But at least you should know that there are some wires which is connecting these banks. And now you can see that if C2, this core is requesting for a block which is in this bank, then it can easily access it, right? It is very near to this. Only this much distance is need to travel. But if this core is requesting for a block which is here in this bank, then it has to travel through this line and is to come here and to collect the block, and it will. So communication length is more. Okay, so that's why in this concept is called NUCA, non-uniform cache access. Why non-uniform? Because the access time of each bank is not fixed. If bank is near, then it will take less time. If bank is far, it will take more time. But one important point you have to remember, all this thing that I'm saying, this entire thing is your CMP, means everything that I'm discussing is within the chip. The wires, the network that I'm saying, it is also within the chip. That's why it is called NOC, network on chip. And it's a big research area. It is also my research area. So maybe as I promised that I will upload some interesting videos, which will be extra lectures. In that extra lectures, maybe I'll upload some concept of NOC and all. So I hope you are getting some idea about how modern cache memory looks like in multiple core. But that's not the end. This is also a very basic, simple design. That design normally don't follow, because you can see there is a common wire is here, right? That common wire is using by C1 and C2. That is also not true. So, but here we assume that this is a design. So in this design, you can see there are multiple banks here. So all are banks. So what I did actually, the same diagram here, the same diagram I simplified here, and you can see all these are small banks. Each is set associative bank, but I'm not showing it here. So now previously when I was only discussing about set associative cache, I was saying this is your set associative cache, and there are only sets and ways. So if I want to map a block, what I explained that first we'll fix a particular set, and I'll say, okay, block will be placed in any of these four positions in set associative cache. But here there are 16 set associative cache. There are 16 banks. So first of all, we have to decide which bank your block will go. Yes, isn't it? So this type of tag is not enough. So what I said that this is a 32-bit address. First part is your offset that I have not explained yet. I'll explain. Last part is your tag, and this part is your index. Based on this index, you decide which set it will go. But only set is not enough. Before set, there are 16 banks. So this index part you have to define bank index and set index. First of all, based on bank index, we'll decide which bank this block will go. You can see 001. So first bank. So I am assuming indexing is starting from 0, 1, 2, 3 like this. So this block will map to bank number 1. So we'll go to bank number 1 first, and then each bank is a set associative cache. So each bank has multiple set. So now this set index will help me to find out which set inside this bank is the location for this block. So this is how it is mapping, and that's why it is called static NUCA. Static NUCA means that the mapping is fixed for a block. If a block is mapping to bank 1, you cannot move that block from bank 1 to bank 5. Suppose your core is here. Okay, your core is here, and core is requesting for a block A, which is placing in this bank according to the mapping policy, according to the mapping policy that I've just explained. Suppose this core is requesting for this block multiple times, very repeatedly. So what will happen? Every time we have to travel through this traveling is must. You cannot reduce it. But somehow if you can move this block A from here to here, then that traveling time will be reduced, right? So in that case, you need to migrate block A from one bank to another. That migration is not possible in static NUCA. That's why it's called static, means mapping of a block to a particular bank is static. You cannot migrate it. So migration is allowed in another kind of design is called DNUCA, dynamic NUCA. Maybe it is here, dynamic NUCA, but I'll not explain dynamic NUCA. Why? Because it's complicated and it's not required for you. That's why I've written DNUCA is not important for you. So there are some slides here for DNUCA. I don't have time also, so I'll not cover it. If you want, you can scroll, but it is not required. In short, DNUCA allows migration. If there is a block here, which is repeatedly accessing by a core C1, which is physically placed here, then there are provision in DNUCA to migrate this block from here to here. So this type of provision is there, but my DNUCA is complicated. You don't need to understand. But yes, if you understand SNUCA, then it will be helpful for you. So I'm skipping all this slide here, which are only for DNUCA. I'll only directly go to jump to last slide, and I'll just take 2 minutes here. So modern day cache memory or modern day processor, there are two ways. One, this is one diagram. In this diagram, you can see in this processor, there are 6 core, P1, P2, P3, P4, P6, P5, P6. There are 6 core. Each core has their own private L1 cache. Okay. And all the cores are sharing a L2 cache here. This is the L2 cache. This is placed in the central location of the chip. And this is L2 cache, and this is also your LLC. Why LLC? Because this is the last level cache. We are assuming 2 level of cache here. And you can see the structure of this L2 cache. The L2 cache is not a single cache. It is divided into multiple banks. So basically the cache is a NUCA cache, right? It is satisfying the NUCA property. It is divided into multiple banks. And now the banks are connected with some interconnect, which is called network on chip, NOC or NOC. So this is one kind of design most of the modern processor follow. Not modern, but till 2015 or 2012, this design was very popular. That there are some core, and in the central location of the chip, place the entire cache divided into multiple banks. But modern days processor use this type of design. This is a tile. I'm saying this red color box. You concentrate on this tile. There is a core here in this tile. There are some L1 cache here. L1 cache normally divides into I cache and D cache, instruction cache and data cache, but it is not required to understand at this moment. You just try to understand that every tile here is a core, a L1 cache and a L2 cache, and there will be multiple tiles here like this. So you can see here there are 16 tiles, and I have just zoomed one tile here. This tile is zoomed here, so each tile has a core, L1 cache, and a L2 cache. So what is this L2 cache here? The L2 cache here is same as this cache in the left diagram. You can see this L2 cache is also divided into multiple bank. This particular L2 cache in left side. The same L2 cache is there in right side also. But now this L2 cache has multiple parts, and one part is assigned to each tile. That is the only difference. And this design is called TCMP, tile based CMP, and most of the modern processors are based on tile based CMP. So I think I need 2-3 minutes more to explain it, but I think today I don't have time. So I'm stopping this lecture here, assuming that this is TCMP. At least you will remember that this is called TCMP architecture, and this is called centralized architecture. Both are CMPs. CMPs means both are multi-processor designed on a single chip. Whatever concept I am saying are inside a single chip. If you purchase the Intel i7 processor, it is built on TCMP architecture. So that is also a TCMP architecture. So I think CMP centralized LLC I have cleared. TCMP architecture, I think 2-3 minutes more I'll take. But so what I'll do, I am stopping this lecture here. So at the beginning of next lecture, I'll explain the TCMP. It will take hardly 2 minutes. So officially, I am closing the introduction part here. And from next lecture, I will start from textbook. So now if you have any question, you can ask now. Any questions? Sanawaj, I think I'll ask, you'll get a proper answer after 2-3 days. I hope you have get a partial answer today, but after 2-3 days, you'll get the full answer. What is the reason behind centralizing the LLC? See, initial reason was you have to place a cache memory somewhere, right? And cache memory, normally the memory size is also, it's not less, it's huge. So the initial design, there was not much intention, but if you place a cache memory LLC in central position, that LLC is shared, right? It is accessing by all the cores. So if you place in a central position, then it will be easy to access by all the cores. That's why it's placed initially in the central location. In Nuka, access always start from the first bank. No, in Nuka, as I said, it's based on mapping, right? So if core is requesting for a data and the mapping is on, the data is mapping on bank 15, then you have to directly go to bank 15 and you will access it. You need to access it. So access will not start from a particular bank. So if you have more doubts on Nuka and all, what I'll do, maybe I'll spend some time during a tutorial session to discuss it. Honestly, this Nuka is not directly connected with your course. In your course, if you understand single core, cache memory kya hai, main memory kya hai, that will be enough. But at least what I am trying to give you, that at least what next after this course, you should be in a position to start doing something else in this direction, right? उस टाइम पे Nuka काम आएगा आपका. So if you want to know something more about Nuka, maybe I'll spend some time during the tutorial session and I'll explain it. और mapping policy वगैरह मैं थोड़ा detail से explain कर दूंगा. Okay. So basic concept how computer works, I'm stopping here. So from tomorrow we'll follow textbook. And now you'll feel that you'll easily understand the basic concept written in textbook because you know how computer works. Okay, so I'm stopping the slides here and also I'm stopping the recording. Thank you for joining. You may leave.